things that we wanted to do in presenting you some material on MPI, again, as Rusty said yesterday, we're expecting that you are at least a little bit familiar with MPI. We want to talk about some of the things that you might not think about as much when you're writing MPI codes, either in terms of the parts of MPI that you use or in terms of how you use it. And I'm going to start by giving you an example of a way to use MPI that has a very unintended performance consequence. I'll give you a heads up. When I finish this, we will only have covered part of the story. I'll cover the rest of it at the end of the day today. So we've talked a little bit about how anytime you synchronize, that means you're holding other people up to wait until you've reached that synchronization point. But you can set things up so that you get sort of unintended synchronizations with the way you write the code. And again, this is a very common issue in performance. And we saw it yesterday in another context, which is where if you write a loop by saying for I equals 0 to n incrementing I by 1, you've essentially added a synchronization point because you've specified that first you do I equals 0, then you do I equals 1, and so forth. And remember this admonition yesterday was don't require that order if you don't need it, that it's very important to convey that you don't actually care which order that was done in, you just cared that at some point it was done. And we'll see the same thing here with MPI. So I'm going to give you an example. This example came from some experience that we had many, many years ago in talking to a group at NASA that had a code, and they were surprised at the poor performance of the MPI communication and wanted to understand what they had done wrong. And so we looked at it and discovered that there's some interesting things that go on that require you to think about how the machine is executing the code. So how many of you have heard the phrase execution model? OK. So I hope by the end of these 2 weeks, you'll have a much better understanding of why you need to know what an execution model is. What you should think of as an execution model is your picture of how the machine operates, as to what it does, what it executes. And that doesn't mean necessarily at a very, very fine grain, but it means with enough accuracy, enough fidelity, for you to reason about the performance of codes. And we're going to see a very simple execution model in the next couple of slides as an example of how you go about thinking about how a parallel code runs. Okay, so let's just look here. We've got, this is going to be a mesh exchange. Think of each of these blue boxes as a local mesh. Let's say it's a 2D mesh. It's regular. This is a node or a process. In fact, this example is so old, a single processor core took up at least one chip, if not two. So just think of this as a process. And the arrows are the communication for the neighbors. And for the sort of typical neighbor exchange, you know that you have data on this edge that you want to send to this process, and data up here you're sending to this process, and so forth. And so it's very easy to write that. And you can write it like this. All right? What's wrong with this code? It's not a rhetorical question. Somebody has to answer. It could deadlock, right? So MPI send has to wait until you can reuse that buffer, the edge buffer there. And so that means that the data has to be at least away from the process that's doing the sending. Well, if the length of that data is very large, the process that's receiving it might not have space for it, or potentially might not have space for it, particularly if lots of processes are sending. And so what might happen there is that send might simply send a message saying, please tell me when I can send this to you. Well, they're all doing that, waiting for somebody to do the receive. So in some sense, this is a nice problem because the code deadlocks. Why is that nice? Also not a rhetorical question. Right? You know that you've got a problem. Right? What are the worst problems? The worst problems are the ones where it's not doing what you think it should do, and you don't know it. Right? So the very worst problems would be you just got an answer, and you use the answer to make some important decision, like what part of the coast to evacuate, and it was the wrong number. Okay, so that's really bad. This one, however, we'll see a different kind of bad example. Okay, so that one deadlocks. I could write the code a little differently, still using the blocking sends and receives. So for example, I could say if I have somebody to send to below me, there's a neighbor below me, do that send, and then I do the receive. In some ways, that code is worse because it will work, but it's completely serial. Because what happens is every process starts doing its send to its neighbor below, but only they have to wait until a receive is issued. Well, there's only one process that can do a receive, which is the process that has no neighbor. So it does the receive. Then that allows the send to it to complete, allowing the next receive to happen, which allows the send to it to complete, and so forth. And so the worst thing about this is the code runs fine. You just think that it's slow, and that's got to be MPI's fault because MPI is fast. So the people we were talking to understood this. They had not written this code. So they had used the non-blocking receive. As Rusty mentioned yesterday, the importance for the non-blocking receive is really for parallel program correctness, not necessarily to give you communication computation overlap. And so they wrote this code. So they posted all the receives, and then they did the sends. Now, what they found was that in fact did not perform well, which was a bit of a surprise. And they did it this way because dealing with a non-blocking routine is a hassle, right? Because it means that you have to set aside a buffer and remember not to manipulate it or touch it until after you've done the wait all. There's in fact a paper, I think it's a Brinch-Hansen paper, explaining why this is such a terrible idea that people who came up with it should never be allowed to do computing. The problem is that you need something like this. And at the library, that's hard to, no one has come up with a better way of writing this. The language level, there is a concept called futures. How many people have heard of a future? Okay, so there is a way that you can describe this that allows a language system to handle some of the issues, to make sure that you don't, in fact, manipulate this buffer while it's still in use. But in the library, you don't have that sort of analysis. Okay, so anyway, we've got this code, and it does not perform well in practice. So how do you understand that? Well, when anything like that happens, what you have to do is what we used to tell students to do. You have to play computer. So what does play computer mean? It means you have to think of your execution model and the simplest possible execution model that will answer your question and see what happens. So here's how our execution model is going to work. I'm going to assume that the sends interleave. That means that the data that's sent is going to be chopped up into pieces and sent down the links. That's the way most of the networks work in some way. I'm just going to look at the sends. The sends are going to control the timing. I'm not going to think about what happens with the receive. I'm not going to assume that the receive pushes back on the sends or something. Receives don't interfere with the sends. And in that case, I've got 4 neighbors. I should be able to do this exchange in 4 steps. Okay. And so let's see what happens. And I should say, remember that first picture, this mesh is a mesh, it's not a torus. And so these edge processes don't have neighbors, there isn't a wraparound. Okay, so here's what starts to happen. So up there at the top, I've got a down neighbor, I send to it. Okay, in 1 step, I'll be able to deliver all of that data. Same for this process, same for this process. Oh, this process doesn't have a down neighbor. So it goes ahead to the next part of its loop, which was to send right. So it starts sending there. Well, the problem is, we come down here, this process does have a down neighbor. It's here. So I've got data coming in from 2 different sources. I'm assuming that I can only send or receive a certain number of words per unit time. And I'm assuming that they're interleaved. So basically, I get half the data from here, but half of the data from here. Now, this is a blocking send. So it basically is now sending at half the rate that you might expect. The same thing happens over here. So this process has no down neighbor. It has no right neighbor. It sends up. That means that it gets about half the data up here. And this process only manages to get half the data down here. So let's see what happens as we continue. Here's our next step. So this process was sending right. It sent maybe half of its data right. It sends the next half. This one was sending down. Managed to send the next half down. Same here and here. Up there, the process in the corner, upper right corner there, it sent down, it was done, has no right neighbor, has no top neighbor, does have a left neighbor, so starts sending that data. Again, that middle process up there has got data coming in from 2 directions. It can't get all of the data from either one of its partners. And so each of those is now sending at about half of the rate that you might expect from a simple ping pong. Continuing, at step 3, these processes have finished like sending right, so they start sending up. This process can send left. Same thing sort of up here. This process finished sending down. It has no right, so it sends up, and so forth. At the very top there, it turns out now that you've got 3 processes sending to that one up there in the middle. And so you're going to get maybe 1/3 of the data rate through from each of those. Now, 2 of those are sort of half done. So they'll make a little more progress. So now we get to step 4. Now remember, if what I did was, in step 1, everybody who was sending down sent down, and only that, then that step would have just completed, because there would have been no contention, no interference. And then in step 2, the ones who were sending right would send right. That would have worked in 1 step. And then 3rd step, send up. 4th step, send left. I would have been done in 4 steps. So here's step 4. Got some processes, some are actually done. Some are sending their last one to the left. Some of them are not yet done because they've been slowed down. So these guys have been slowed. This guy in particular has been slowed down. So now I go to step 5, and I have to finish up these. Again, this is sort of half the rate and half the rate. And finally, in step 6, these last 2 processes, the ones with 4 neighbors, send to the left. So instead of taking 4 steps, this took 6, slow down at 50%. Now, this is with a fairly simplified, abstract execution model, but it shows me what's going on. It shows me in particular that by requiring the communication to complete in a certain order, so by using send instead of I send, I said each of those sends must complete before I can begin the other. And what that means, to sort of go back, is that, like in cases like this process has data to send left, but I've said it's got to finish this first. But because this one is sending data to another process that's getting data from another place, the rate at which I can get that data out is lower. And so it just sort of sits around half the time. If I said, I just want to do all those sends, and you send whatever you can send, it could start sending data this way as well. And so by requiring a particular order of execution, I've slowed down the code. And you can see that here on this chart. This is a barrier to make sure everybody's starting at more or less the same time. These blue bars are the sends. In each case, in this example, the same amount of data is being sent. And so each of these blue bars should be the same length. What you see is that some of them are about twice as long as the others. And twice as long as the others because they're sending at half the rate. Also the case that the processes that finish last in this case are the ones that this example would show. This is on the same number of processes, so there's 12 processes here. And so process 1 finishes last. Whoops. 0, 1, 2, like that. OK. So there's actually a couple of interesting things here. You also look at the distribution of send time. So this is not as clean as our execution model would suggest, but you've got the fast time. This is about, say it's about 3.5. Somewhere between 6 and 7, you've got another little peak. It's a little split here. So this is like close to the double. This is the triple, where the 3 processes were sending to the same one. Right? So the key thing here is using the sends, which this team used because making sure of that the buffers were untouched meant making copies, meant managing all of that. Doing it for the I receives was painful enough, so they just wanted to do the minimum possible. Very understandable. But what it means is that by doing the sends as blocking sends, they imposed an order of completion that caused the performance to drop significantly. In this model, again, by about 50%. And in the runs we were doing on a machine similar to the ones they were running on, it was an IBM SP, also communication time of about 50% loss. Note, this is not so much a message passing thing. If you were using memcopy to do copies between memory and different cores in the same chip, or between, if you do a remote copy to other processes using a PGAS model or a one-sided programming model, it's the movement of data where you're going to contend for some resource that is the problem. And a memcopy or a blocking move in PGAS is blocking. And so the key is that if you impose a synchronization, impose a completion order, and you might have some contention for the communication resource, you run the risk of having loss of time. Now, as a sort of interesting aside, on a machine that has a very, very fast barrier, so a system that has, for example, hardware support for barriers, so in a handful of cycles, you could do a barrier. There is a fix for this, which is anyone know what the fix would be?
Lockstepping,
Yeah, so I could do the send and then do a barrier. And that way, only the sends down would happen. That I'd wait at the barrier before starting a send in the next direction. So if I went, I'm not actually advocating this, but you will see this sometimes in code. So if I did right here a MPI barrier, and the barrier was fast enough, this code would be faster. So there are times when barriers can speed up code by eliminating contention in your communication layers. And so again, if you see code that has been used on a system with a really, really fast barrier, like some of the blue jeans, you might see those barriers. And we usually say barriers are slowing your code down. And that's often the case, even in systems with a fast barrier. But there can be cases where by controlling the order of communication, they speed things up. Okay, so go back here. So the fix was just to bite the bullet and do the ISEND for all the communication. Then essentially, all 4 steps look like this, where you're using all of the links at the same time as data is going, for example, down here, and it's getting data from other places. Well, you're also sending data out to your neighboring processes. It results in a plot that looks like this. Now notice that instead of process 1 being the one that finishes last, it's these 2 processes. Those 2 processes are these 2 processes, which are the only ones with 4 neighbors. So it's exactly what you expect. Okay. So the lesson here, and again, it's not restricted to message passing. For almost all of these things, whether you're dealing with communicating with another process, or you're dealing with communicating with memory, different hierarchies of memory, or communicating with the I/O system, is to defer the synchronization, to impose as little order as you can, and allow the system to order the operations most efficiently. So everything you do to impose an unnecessary order can impact your performance. Okay? And so easy way to do this in MPI is to be good about using the non-blocking operations and to use MPI wait all or wait any or wait some to say, OK, at this point, I in fact need things to complete. And so for a Halo exchange, the easiest thing is to do a wait all. So do all the communication, then wait for all to complete. If it turns out that that's not good enough, you can take that one more step and use, for example, wait any or wait some, and complete, find out what data has completed and then deal with it, giving the system yet more time to complete the rest of the communication.